Hello, everybody. Happy Halloween. All right, so we're talking about balanced binary search trees. We've been talking about binary search trees. We've been talking about trees, binary trees, which are every node has 0 to 2 successors and 1 predecessor except for the root. We talked about binary search trees in which all the data to the left is less than, and all the data to the right is greater than the data of any node in the tree. And now we're taking it one step further, and we're going to talk about balancing our binary search trees. Well, why do we want to balance our binary search trees? Well, okay, so let's talk about this. Finding. Well, in lists, when we were finding, it could take O of n to find data, which is awful. Ugh, ugh, we don't like that, right? We might have to go through every single piece of data. Ugh, we don't like that. So then we have binary search trees, where each node has 0 to 2 successors, and for every node, the data to the left is less than the data in a node, and the data in the right child is greater than the data in any node. And in that case, finding can be a lot faster. So here we have an example of a binary search tree. All the data for every node is less than, and all the data for every node is to the right of is greater than the data in, oh, all right, let me introduce you. This is the latest member of our family. He doesn't have a name yet. He will probably be walking on the keyboard at some point because he's a little mischief maker. We just got him last night. So yeah, so as I said, he's our newest member of our family, and he's probably going to cause issues as we go. All right, so every node to the left is less than, every node to the right is greater than. So let's say we want to do something like find 32. Okay, well, we start at 24 because you always start at the root. 32 is greater than 24, so we go to the right, we go to 36. Just by doing that, we've eliminated all this data. I never have to look at any of this data, all that, right? So I've eliminated half my data just by making that simple choice. Okay, so now we're at 36. We're going to go to the left because 32 is less than 36, so we go to 29. By doing that, we eliminate all of this data here. It's just gone. We get rid of all that data. Once again, we've eliminated half of the remaining data. So now we're at 29. We make the decision to go to the right. We go to 32. We find 32. But again, we would have eliminated half of the remaining data. So if every choice you make, you eliminate, you never have to look at approximately half the remaining data in a good binary search tree. So let's break it down. With n being the number of nodes in the tree, and k being the number of levels of the tree. So in this case, there are 4 levels to this tree, okay? If n is between 2 to the k minus 1 and 2 to the k, at most, it will take k steps to find any node in the tree. That is log base 2 of n, okay? Every comparison should eliminate approximately half our data. There's a cat climbing up my leg at the moment, and he has very sharp claws. Okay, here we are. Yeah, he's never going to stand still. If the tree is balanced. So as long as the tree is balanced, we're going to be eliminating about half the data every single time we make a decision. Here's an example of a binary tree gone wrong, right? Is this a binary tree? Well, let's look at it. Every node has 0 through 2 successors and 1 predecessor, okay? For every node, the data to the left child is less than, and the data in the right child is greater than the node. Yeah, that's true too. This is a binary search tree. It is an unbalanced binary search tree, massively unbalanced binary search tree, but it is a binary search tree. The problem is, in this case, if I wanted to find 55, there are 11 nodes in this tree. I would have to look through all 11 nodes to find 55. In essence, it's a linked list. And in essence, the running time of find is going to be n, which is awful. Ugh, right? We don't like that. Okay, so what we want to do is we want to maintain balance. All the cats are coming to see me today. I think we're all sort of a little off our game. So what we want to do is we want to maintain our balance, okay? And there's more than one way, more than one system for maintaining a balanced binary search tree. red-black trees, they're pretty common. B trees are pretty common. 2-3 trees. The way we're going to learn is AVL trees. All of these maintain balance in a binary search tree. They do it slightly different ways. We're going to be looking at AVL trees. And if balance is maintained, that means that inserting, deleting, and find can all be done in log base 2 of n time. Okay, so what's an AVL tree? Named after Addison, Velsky, and Landis. They're balanced binary search trees. And in an AVL tree, every node is balanced. The height of the left and the height of the right subtrees differ by no more than 1. That's the definition of balanced. The definition of balanced is the height of the left subtree and the height of the right subtree of each node differs by no more than 1. So to find the balance of a node, we take the height of the left child, we take the height of the right child, and we subtract the height of the right child from the height of the left child, okay? In an AVL tree, the order matters. You must subtract the right child from the left child, okay? What we're looking for, well, we want to always subtract the right child from the left child. The order matters. Now, the other thing I want to point out is, and this is something, trees, when we look at a tree, we see the tree holistically. We see the whole entire thing, right? So we can kind of look at it and we can kind of go, yeah, it looks pretty balanced to me. I'm good with it. Or like, ugh, no, that's just not balanced at all. We can kind of just tell by looking at it. Remember, computers aren't humans. They can't do that. A computer, the information a computer has at any given moment is the information inside a node. So it looks at one individual node at a time. And what that means is, if it's looking at this node, the only information it has is the left child, the address of the left child, the address of the right child, the address of the parent, and any data inside that node, okay? So that's why it's kind of nice that we actually stored the height of the left child and the height of the, like the height of each node inside of the node itself, because that makes it easier for us to calculate the balance of each node. It's really hard to concentrate with a little kitten crawling up your leg with its little claws. All right. So AVL trees are binary search trees, okay? That means that find is done just like we always did it. Traversals, pre, in order, post order are done just like we always did it. And they do pretty much the same thing. Where the differences lie are in insert and delete. Because when we inserted and when we deleted, that's where the heights of a node changed. And if the heights of a node changed, that means that the balance of its parent could change, okay? If the height of a node changed, that means the balance of its parent could change. So when we insert and when we delete, that's when we want to look at the balance of each node in the ancestor path up to the root. If we find something is unbalanced, then we must do something to restore the balance. What are we going to do? We'll talk about that later. Okay. But here, down here, we have this lovely tree. If we look here, I'm just going to do this side over here. 54. The left child has a height of 0. The right child has a height of 1. So the balance of 54 is going to be 0 minus 1, which is going to be negative 1. Okay. Here, 72. The left child has a height of 2. The right child has a height of 1. 2 minus 1 is 1, so the balance of 72 will be 1. 50, the height of 17 is 3. The height of 72 is 3. So 3 minus 3 is 0. So the balance of 50 will be 0. Okay? Excuse me, I got caught in my throat. So this is an AVL tree because every single node in this tree, the height of each node differs. The height of the left child and the height of the right child of each node differ by no more than 1. Okay. So here we have an example. Okay. We look at this. What is the height of each node? Well, the height of 8 is 1. The height of 13 is 2. The height of 7 is 1. The height of negative 8, negative 13. The height of 13 is 2. Height of 15 is 1. This is 2. This is 1. So 14 is going to have a height of 3 because it's the max of the 2 plus 1. Height of 6 is going to be the max of these 2 plus 1. So this has a height of 2. This has a height of 3. It's going to be 3 plus 1. The height of 6 will be 4. What is the balance of each node? Well, the leaves are always going to be 0 because they have no children to the left and no children to the right. So they're going to be 0. So this balance is 0. Here, this balance is negative 1 because it has 0 height to the left and 1 height to the right. So that's negative 1. Here, this one has a height of a balance of 1 because this has 1 and this has 0. So 1 minus 0 is 1. Here, this has a height of balance of 0. This has a balance of positive 1 because this has a height of 2. This has a height of 1. The left minus the right will give us a height of 1, a balance of 1. Oh, Lord. Balance of 1. And then finally this one. Well, this has a height of 2. This has a height of 3. 2 minus 3 is negative 1. So the balance of 6 is negative 1. All right. So now we're going to insert negative 9, right? Go to 6. Negative 9 is less than 6. Go to negative 13. Negative 9 is greater than negative 13. Go to negative 8. It's less than 8, so it'll be inserted here. Oops. Okay, so now that we've inserted negative 9, this is going to have a balance of 0 and a height of 1 and a balance of 0. Now that we've inserted 9, we have to check on 8. Okay, so 8's height changes because now this has a height of 1 and this has a height of 0. The max of the 2 is 1 plus 1. It's going to have a height of 2. And its balance changes because the height of this is 1. The height of its right child is 0. The non-existent right child is 0. 1 minus 0 is 1, so its balance is 1. Okay, now we go to its parent. Okay, the height of this changes, becomes 3, but also the balance changes because the balance of its left child is 0. The balance, oh goodness, the height of its left child is 0. The height of its right child is 2. 0 minus 2 is negative 2. So negative 13's balance is negative 2. That means this is unbalanced. This is our unbalanced node right here. And it's caused by the fact that we just inserted negative 9. Now, if we were doing our AVL tree, we would fix this. But for now, let's just keep going up. Now, this has a height of 3. Height of 3 minus a height of 3 is 0. So the balance of 6 is going to be 0, and the height doesn't change because it was already had a height of 3 here. Okay. But this is our problem here. This is where we have an unbalanced node. This is where our AVL tree is no longer an official AVL tree. Okay, so takeaways. Okay, so there are more than one binary search tree. There are many balanced binary search tree algorithms, and we're just learning AVL tree. That's one we're learning. Okay, AVL maintains its balance by keeping track of the balance of each node as we insert and delete. So balance, what is balance? Balance is when the height of the left subtree and the height of the right subtree of a node differ by no more than 1. And the balance is calculated by taking the height of the left child and subtracting the height of the right child. And it is always done in that order, okay? Balance changes when we insert and when we delete. And the reason the balance changes when we insert and delete is because that's when the height changes. And we have to worry about the balance of the height and the balance of the ancestors. That's what we're worried about. We don't have to worry about the rest of the tree. All right, so what do we do when we have an unbalanced node? It's coming.